Good morning. Today's topic is Hall effect. The carrier concentration in a semiconductor may be different from the impurity concentration because the ionized impurity density depends on the temperature and the impurity energy level. To measure the carrier concentration directly, the most commonly used method is, as we all know, the Hall effect. Hall measurement is also one of the most convincing methods to show the existence of charge carriers because the measurement can give directly the carrier type. We show in our diagram that when an electric field is applied along the x-axis and a magnetic field is applied along the z-axis, then what happens? If we consider a p-type of semiconductor, the sample is p-type semiconductor, the Lorentz force on this will be qv cross p, which is equal to qvxbz. Due to the magnetic field, it will exert an average upward force on the holes flowing in the x direction. The upward directed accumulation of holes at the top of the sample that gives rise to downward directed electric field Ey. Since there is no net current flow along the y direction in the steady state, the electric field along the y-axis exactly balances the Lorentz force, that is Q Ey is equal to Qvx Bz. Ey is equal to Vx Bz. Once the electric field Ey becomes equals to Vx Bz, no net force along the y direction is experienced by the holes as they drift in the x direction. The establishment of electric field is known as Hall effect. The electric field is called Hall field and the terminal voltage Vh, which is equal to Eyw, is called the Hall voltage. For the drift hole velocity, the Hall field Ey becomes equal to Jp divided by Qp into Bz, that is equal to RH Jp Bz, where RH is equal to 1 upon Qp. The Hall field Ey is proportional to the product of the current density and the magnetic field. The proportionality constant RH is the Hall coefficient. A similar result can be obtained for n-type semiconductor except that the Hall coefficient is negative. RH is equal to minus 1 by Qn. A measurement of the Hall voltage for a known current and magnetic field yields P is equal to 1 by Q RH, which is equal to Jp Bz divided by Q Ey. This is equal to I Bz divided by Q Vh divided by W. This finally becomes equal to I Bzw divided by Q Vha, where all quantities of the equation can be measured. Thus, the carrier concentration and the carrier type can be obtained directly from the Hall measurement. Thank you.